My name is Eunju. I'm going to start the topic of the study on optimal deployment of tsunami observation instruments in Korea. Tsunamis are one of the most destructive coastal hazards in the world. Tsunamis occurred in both 2011 and 2018, resulted in massive casualties and property damage. According to the historical occurrences of tsunamis have been generated worldwide. To reduce damage, tsunamis are monitored through different types of techniques. For the early warning purpose, NOAA and Japan offers their own systems using buoy and bottom-mounted sensors. Besides, tsunamis generated on the west coast of Japan damages coastal city on the east coast of Korea in 1983 and 1993. In recent years, there has been increasing interest in the potential tsunami zone near the west coast of Japan. Therefore, Korea needs to have offshore tsunami observation instruments in proper locations for tsunami detection and warning aspects. According to the Lee et al., the Korea Meteorological Administration issues tsunami warning using coastal surge gauges and tidal gauges. Especially a Ulleungdo surge gauge located in the East Sea plays a critical role in tsunami hazard mitigation of the Korean peninsula because it can confirm the approach of tsunamis 30 minutes or more before they impact the eastern coast. However, these instruments are located in coastal areas, so it is difficult to issue advanced tsunami warnings for the coastal areas in the Korea, including Ulleungdo. To better anticipate potential tsunami generated on the west coast of Japan, this study proposes the optimal region for offshore tsunami instrument deployment under the limited condition that the tsunami sources are in out of the territorial sea. This figure shows the steps and considerations used to determine an optimal deployment region for offshore tsunami observation instruments. First, we should maximize detection probability with minimum instruments. Second, we should maximize evacuation time. Finally, we consider tsunami source inversion with instruments in the future. This is the flow chart of this study. First, we calculated tsunami propagations using both potential tsunami scenarios and numerical modeling, and we accepted the result of numerical modeling if the water depth is lower than 300 meters, because according to the Mulia et al., tsunami waveforms recorded at such locations are usually inadequate to infer the tsunami source due to the coastal morphology effects. Thirdly, we find higher probability area in eastern territorial sea of Korea for tsunami detection under the various rupture parameters. The rupture parameters include source location, strike angle, dip angle, and slip distribution. After narrowing down the probability area, we applied two specific criteria from previous studies: maximization warning time and installation conditions. This study only deals with the ocean bottom slope angle as an installation condition. Finally, we will propose a region that meets all conditions as optimal region for offshore tsunami instrument deployment. According to the Mulia et al., both potential tsunami scenarios and numerical modeling are used to design future tsunami instruments. In this study, we used 39 potential tsunami scenarios in which all sources are near the west coast of Japan. To figure out the optimal region for tsunami observation instrumentation, this study only focused on the potential tsunami scenarios that can affect the east coast of Korea and used in previous studies. And to calculate 39 potential tsunami propagation into the eastern sea of Korea, we used the Cornell multi-grid corporate tsunami model, so-called COMCOT. This model has been used for many tsunami propagation and inundation studies. And the Korea Meteorological Administration used COMCOT as its standard model for tsunami warning and hazard prediction. So we used COMCOT to numerically calculate tsunami propagation in the eastern sea of Korea to predict tsunami occurrence and propagation based on the 39 scenarios. The input information of numerical modeling is indicated in this table. This is result from numerical modeling with tsunami scenario case 4. After calculating tsunami propagations, we only consider results in this column map area where the water depth is below 300 meters, so that tsunami waveforms are not affected by the coastal morphological effect. According to Milia et al., tsunami observation instruments should be placed in regions where energetic tsunami-related dynamics occur. So, previous studies used EOF spatial analysis and overlaid maximum tsunami wave height distribution to figure out the area where tsunami energy converges. In this study, to confine the higher probability areas, we used the maximum likelihood estimation, so-called MLE, instead of EOF spatial analysis, because MLE is more cost-effective. The standard MLE approach is called the frequentist method. This method has been widely used for optimizing parameters that best fit the joint probability of the given data. So, in this study, MLE was applied to determine a location in the eastern sea of Korea with a higher likelihood of tsunami propagation with 39 maximum tsunami wave height distributions. This is the result of application MLE. The Korea issues tsunami warnings when there is an earthquake greater than magnitude 7 and tsunami height reaches 0.5 meters or higher at the Korean coast. Considering the effect of coastal morphology, this study estimates the probability of a 0.1, 0.2, or 0.3 meter higher maximum tsunami height passing through each grid. So the probability of tsunami propagation above each standard wave height were calculated. And then MLE results of each standard wave height were obtained by the sum of the log probabilities. The location where has higher MLE matches the higher tsunami detection probability area because tsunamis propagate with different parameters more frequently in this region. According to the OCCAR, it is the most effective way that the tsunami warning center gets maximized warning time to reduce the damage from the tsunamis. Offshore instruments located in high probability detection areas are not necessarily enough to maximize warning time, so we investigated how to further optimize instrument deployment region to include maximized warning time. Warning time estimation were adopted from previous studies and can be calculated using this equation, where WT warning time is for a specified coastal line, TTT is travel time to coastal line, and DD, DTR, and DC are the tsunami instrument detection delay time, data transmission from the instruments to the tsunami warning centers, and tsunami warning centers confirmation time respectively. We set the input of equation based on the historical information and previous studies. According to the result of equation, offshore tsunami observation instruments should detect tsunami components within 1.5 hours after the earthquake. The red in this figure indicates the area which maximizes warning time. By multiplying the probability of tsunami propagation and the probability of tsunami travel time less than 1.5 hours after earthquake, the optimal area of the tsunami observation instrumentation in the eastern sea of Korea was identified as shown in these figures. Results suggest that the northeast of Ulleung-do is the optimal offshore region for instrument deployment. An additional consideration is physical installation for the bottom-mounted sensors. The instruments should be located in a safe area to avoid earthquake destruction. However, this study only considered potential tsunami scenarios on the west coast of Japan. So we focused only on a flat ocean bottom slope as the installation condition. We calculated ocean bottom slope using both MATLAB and the GAPCO real bathymetry data. The standard allowable ocean bottom slope for installation is less than 8 degrees. This figure indicates the ocean bottom slope angle of the area near the higher probability area. Finally, this figure shows the example result of colored map for optimal instrument deployment region that meets all conditions. This is the summary. We concluded that the northeast area around Ulleungdo Island is the optimal region for installing offshore instruments. 3 major steps of research are listed. First, we defined a high probability area for tsunami detection using numerical modeling based on 39 potential tsunami scenarios. Second, we defined the probability area of maximum warning time by considering tsunami travel time, the delay time of detection, data transmission time, and measurement confirmation time. And specify the probability map for the optimal region of offshore tsunami instrument by the product of the probability of tsunami detection and warning time. Finally, we considered the bottom slope required for tsunami instrument installation. This approach in this study successfully identified the optimal area for instrumentation in the case that the tsunami source is far from the territorial sea. This study provides the framework for the guidance of offshore instrumentation in the Korea tsunami warning system. Finally, these contents are in the paper. You can find this paper on the Applied Sciences website. Thank you.